So far, we have handled natural number exponents. For example, something like x cubed. We define that to mean x taken as a factor 3 times, x times itself 3 times. In this way, we defined natural number exponents. Later on, we had certain rules which worked for natural number exponents. For example, x squared times x cubed was equal to x to the 2 plus 3, or in general, x to the a times x to the b was equal to the x to the a plus b. If the bases were the same, we kept the base and we added the exponents when we multiplied. Okay, certain rules which held for natural number exponents. X squared times x cubed gave us x to the 5th power. There were 2 x's here when we wrote it out, and then 3 multiplied, so we had a total of 5 x's multiplied together. Okay, now, we had a whole set of rules, and in order for these rules to continue to make sense, when we moved on to 0 exponents and integer exponents, negative whole number exponents, we defined x to the 0 to be equal to 1 if x was not 0. We also defined x to a negative power, for example, x to the minus 4 power, to be equal to 1 over x to the 4th power. X to the minus a was defined to be 1 over x to the a. By defining negative exponents, negative integer exponents this way, and 0 exponents that way, the rules for exponents that we developed for natural numbers were still true. Okay, so we had a set of rules for integer exponents. And now we are looking to extend our understanding of exponents to include fractions or rational number exponents. Okay, but once again, we want the rules that we already have established to continue to hold true. We don't want one set of rules for integer exponents and another set of rules for rational number exponents. Okay, so the rules that we've had should still hold true. The question is, how should we define something like 9 to the 1/2 power? Here we have a fractional exponent, an exponent of 1/2. Well, if the rules that we already have are going to hold true, then whatever 9 to the 1/2 is, 9 to the 1/2 times 9 to the 1/2 should be equal to 9 to the 1/2 plus 1/2, or 9 to the 1, or just 9. This is the rule that x to the a times x to the b is equal to x to the a plus b. We keep the same base and we add the powers. Now, this was a rule, as I mentioned over here, that was true for natural number exponents. You were able to multiply, if you're multiplying and they had the same base, you kept the base, you add the powers. So whatever 9 to the 1/2 is going to mean, we would like this rule to continue to hold true. Therefore, 9 to the 1/2 is a number which, when multiplied by itself, gives us 9. Okay, so two possible answers come to mind. 9 to the 1/2 might be equal to 3, since 3 times 3 is equal to 9. Or you could say 9 to the 1/2 is equal to minus 3, since minus 3 times minus 3 is also plus 9. Okay, now, in mathematics, we do not like to have a symbol doing double duty. Okay, we don't want 9 to the 1/2 to both be 3 and minus 3. So arbitrarily, we will say that whenever I have 9 to the 1/2, I will take that to be plus 3. That is, 9 to the 1/2 will be the positive number, which when multiplied by itself gives us 9. Okay? There is nothing, we could have defined it this way, but this is the traditional way to define it. And we will be consistent, we will stick with this. 9 to the 1/2 is the positive number, which when multiplied by itself gives us 9. 9 to the 1/2 must be, of course, plus 3. Okay, now we could have also done something like this. How should we define 8 to the 1/2? Well, 8 to the 1/2 times 8 to the 1/2 must be equal to 8 to the 1/2 plus 1/2, or 8 to the 1. In other words, 8 to the 1/2 must be that positive number, which when multiplied by itself gives us 8. Now, while 9 to the 1/2 happened to be 3, 8 to the 1/2 is not a rational number. Okay? It is an irrational number. It is a decimal which, it can be written as a decimal which never terminates and never repeats. It's going to be a little under 3, because 3 times 3 would give us 9, so it's going to be a number less than 3. We're not concerned at the moment with what the actual decimal representation of the number is. Still, we take the same understanding that a to the 1/2 should be that positive number which, when multiplied by itself, gives us 8. And in general, we could say, well, how should we define a to the 1/2? A to the 1/2 times a to the 1/2 has to be equal to a to the 1/2 plus 1/2, or a, if the rules that we already have for working with exponents are going to continue to hold true. So a to the 1/2 must be that positive number, which when multiplied by itself gives us a. Okay, now there is another symbol that we can use to represent this. For example, 9 to the 1/2 can also be written as 9 with a little house sort of around it. We call this a radical sign. 9 to the 1/2 can be written as the square root of 9, and this is 3. This symbol, this is read the square root of 9, and when you don't see a sign in front, the positive sign is assumed to be there. Okay? If you just see the square root of 9 or the radical sign with a 9 inside, the positive square root of 9 is assumed. The positive number which, when multiplied by itself, gives us 9. The positive square root of 9 is plus 3. Similarly, a to the 1/2 could be written this way: the positive square root of a. That positive number, which when multiplied by itself gives us a. Okay. Remember, 9 to the 1/2 can be either written positive square root of 9 or just square root of 9. If you see nothing there, it means the positive square root. This is plus 3. If I wanted minus 3, I would say the negative of 9 to the 1/2. This would mean the negative square root of 9, or minus 3. 9 has two square roots, a plus 3 and a minus 3. Okay, when you just see the radical sign, this refers to the positive square root. If you want the negative square root, you will have to write that explicitly, negative square root of 9. Okay, now don't confuse the negative square root of 9 with, say, negative 9 to the 1/2, or the square root of negative 9. This is not defined in the real number system. Okay? There is no real number. There is no real number that satisfies this condition that when multiplied by itself gives us minus 9. Okay, remember, the square root of 9 meant a number which when multiplied, the positive square root of 9 is the positive number which when multiplied by itself gives us 9. Here we'd want a number, or a positive number, which when multiplied by itself gives us minus 9. And there is no such real number. If you take a positive number times itself, clearly the result will be positive. A negative number times itself, the result will be positive. 0 times itself, of course, is 0. So there is no real number which when multiplied by itself gives us minus 9. Okay. The negative square root of 9 is minus 3. The square root of minus 9 is not a real number. Okay? So we will not be writing things like this. We cannot take square roots of negative numbers. The answer would not be a real number. Okay, let's continue with this. (16 to the 1/2 power would mean that number, positive number, which when multiplied by itself gives us 16, or plus 4. It could also be written the square root of 16. The positive square root of 16 is plus 4. Okay? If you want the negative square root of 16, that would be minus 4. But the square root of minus 16 is not a real number. Okay, well, that takes care of an exponent of 1/2. We sort of had an understanding of what we mean by, say, 9 to the 1/2 power. Let's now consider a power of 1/3. What do we mean by, say, 8 to the 1/3 power? We're trying, remember, to handle rational number or fractional exponents. We considered an exponent of 1/2. Now we're considering an exponent of 1/3. In order for our rules for exponents to continue to hold true, 8 to the 1/3 times 8 to the 1/3 times 8 to the 1/3 must be equal to 8 to the 1/3 plus 1/3 plus 1/3, or 8 to the 3/3, or 8 to the 1, or just 8. That is, 8 to the 1/3 must be that number which, when multiplied by itself 3 times, gives us 8. This particular example, we can figure out exactly what 8 to the 1/3 is. 8 to the 1/3 must be 2, because 2 times 2 times 2 is equal to 8. 2 times 2, that's 4, times 2 gives you 8. We can also write this in another notation. We can say 8 to the 1/3 represents the cube root of 8. Okay, we can write it this way. The cube root of 8, and that's 2. Before we had 9 to the 1/2, and we said that was the square root of 9. The positive square root of 9, and that was plus 3. If you don't see any number in the radical sign, okay, the 2 is implied. So although I did not put a 2 in there, when you see it by itself, okay, nothing in there, the index is assumed to be 2 when we're talking about square roots. Any other index would have to be explicitly stated. This is the cubed root of 8. That is that number which, when multiplied by itself 3 times, gives you 8. This is the square root of 9. That is a number which, when multiplied by itself twice, gives you 9. Okay, 8 to the 1/3 I could figure out exactly. 9 to the 1/3, I don't know precisely what that's equal to, but I do know that 9 to the 1/3 times 9 to the 1/3 times 9 to the 1/3 must be equal to 9 to the 3/3, or 9, if our previously given rules for exponents are going to hold true. So whatever 9 to the 1/3 is, it's a number, it's a little over 2, since 2 times itself 3 times gives you 8. Something a little over 2 times itself 3 times would give you 9. It is an irrational number. That is a number whose decimal representation never terminates, never repeats, goes on forever. It is, what it's exactly equal to is not important. The important thing is 9 to the 1/3, or the cube root of 9, means that number which, when multiplied by itself 3 times, gives you 9. And we can say here that a to the 1/3 is the cubed root of a. Just like a to the 1/2 was the square root of a. It could be written this way or like that with the 2. The 2 can be put in or left out. Generally, it's left out. And we can continue this idea and define what we mean by a to the 1 over n. Our a to the 1 over n power must be that number which, when multiplied by itself n times, gives you a. If a to the 1/2 is a number which, when multiplied by itself twice, gives you a, and a to the 1/3 is a number which, when multiplied by itself 3 times, gives you a to the 1 over n is that number which, when multiplied by itself n times, gives you a. And we can write it in radical notation as the nth root of a. Okay, now just a word here. There is a slight difference between even roots and odd roots, okay, in the sense that, well, first of all, if you're talking about even roots, we must have a greater than or equal to 0. You cannot take the even root of a negative number. Okay, if n is even, okay, we will assume that a is greater than or equal to 0. Let me show you some examples. The square root of 64, meaning the positive square root of 64, is plus 8. The square root of minus 64 is not a real number. There is no number which, when multiplied by itself twice gives you minus 64. On the other hand, the cubed root cube root of 64 is 4. Since 4 times 4 times 4 is 64. And the cube root of minus 64 is minus 4, since minus 4 times minus 4 times minus 4 gives you minus 64. So there is no difficulty with a cube root or any odd root of a negative number. The cube root of minus 64 is minus 4. This means I want a number which, when multiplied by itself 3 times, gives me minus 64. If I start with a negative and I multiply it by itself 3 times, I will wind up with 3 negatives, which gives me a net result of a negative. Okay, so that can be accomplished. The square root of minus 64 I can't do. I can't come up with a number which, when multiplied by itself, gives me a negative result, because plus times plus would give me plus, and minus times minus would give me plus. So I can't do it an even number of times and come out negative, but I can do it an odd number of times and come out negative. So over here, when we talk about the nth root of a, if n is even, a square root, a fourth root, an eighth root, whatever, we'll assume that we're talking about even roots of non-negative numbers. Also, when n is even, assuming that a is greater than or equal to 0, we wind up with more than one answer. In a sense, if you were to say, well, 9 to the 1/2 could be, remember we originally said it could be 3 or minus 3. We arbitrarily said it was going to be plus 3. This doesn't come up with the cube root. The cube root of 64 was 4. It wasn't minus 4 also. The cube root of 64 was 4. 4 times 4 times 4 was 64. You could not say minus 4 is a possible answer, so there was no ambiguity. But with the square root of 64, you might say, well, plus 8 or minus 8. Minus 8 times minus 8 gives you 64. Plus 8 times plus 8 gives you 64. So with even roots, we'll have to say we're talking about the positive quantity, which, when multiplied by itself, gives you the square root. Gives you, say, in this case, 64. Okay, so let me write that down for you. A to the 1 over n is the nth root of a. This represents the quantity which, when taken as a factor n times, gives us a. Okay, the quantity which, when taken as a factor n times or multiplied by itself n times, gives us a as a result. And if n is even, we will mean the positive quantity, which, when taken as a factor n times, gives us a. Okay, when we talk about this quantity, and there's no trouble if n is odd if you're taking a cube root or a fifth root, but if n is even, okay, we will assume that we're talking about the positive answer. (27 to the 1/3). Let's try some examples. 27 to the 1/3. This is a number which, when multiplied by itself 3 times, gives us 27. Also can be written as the cube root of 27. This is, of course, 3. (32 to the 1/5). Okay, you can put parentheses in or leave them out as long as it's clear. 32 to the 1/5. This is the fifth root of 32. I am looking for a number which, when multiplied by itself 5 times, gives us 32. This particular one happens to come out exact. It's equal to 2. Since 2 times 2 times 2 times 2 times 2 equals 32. 1/16 to the 1/4 power. I'm looking for a number which, when multiplied by itself 4 times, gives us 1/16. Because we are talking about here, this is the 4th root of 1/16. There could be some questions, so I'm taking the positive answer. Okay, this is the 4th root of 1/16. I am talking about the positive number, which, when multiplied by itself 4 times, gives us 1/16. The answer is 1/2. Because 1/2 times 1/2 times 1/2 times 1/2 gives us 1/16. Now, minus 1/2 times itself 4 times would also give us 1/16, but as I mentioned before, if n is even, we will take the answer to be positive. If n is even, we will mean the positive quantity, which, when multiplied by itself that number of times, gives us what's under the radical sign. Now, I just want to remind you of certain rules that we've had for working with exponents. And our definition for rational exponents was such that these rules will still hold true. So if a and b are real numbers, and r and s are rational numbers, and a and b are positive when even roots are indicated, we have the following rules. A and b are real numbers, and r and s are rational numbers, and a and b are assumed to be positive when even roots are indicated. We have the following rules, which we've had before for integer exponents. They are now going to hold true for rational number exponents. A to the r times a to the s is equal to a to the r plus s. You can keep the base and add the powers. This is how we originally picked our definition for the fractional exponent, so that this rule would still hold true. A to the r to the s is a to the rs. A to the r over a to the s is a to the r minus s. When you divide, you subtract the powers. A to the minus r is once again 1 over a to the r. A to the 0 is 1. In these, we will assume that a is not 0, because we wouldn't want to have division by 0. So in all of these, we will assume that a is not 0. And the definition for a to the 0 equal to 1, once again, was also only if a was not 0. 2 more rules. AB to the r was a to the r times b to the r, and a over b to the r, a to the r over b to the r. The first one you're familiar with. If you multiply, you keep the base, you add the powers. Here, don't confuse these two. Here we are taking a to a power to a power. Notice that the base here appears twice, here it only appears once. You keep the base and you multiply the powers. When you divide, you subtract the powers. A to a negative power, even if it's a fraction, is still going to be defined to be 1 over a to the positive power. A to the 0 is 1, assuming a is not 0. If you have a product to a power, you can take each factor to that power, and a fraction to a power. It's the numerator to the power over the denominator to the power. Here, of course, we're assuming b is not 0. And in all cases, we're assuming that we're never taking even roots of negative numbers. Okay, so let's say we wanted to come up with a value for 27 to to the minus 1/3 power. We wanted to evaluate that. That can be handled by saying 27 to the minus 1/3 power is 1 over 27 to the 1/3 power, using the fact that a to the minus r is 1 over a to the r. 27 to the 1/3 power, of course, refers to the cube root of 27. That is, that number which when multiplied by itself 3 times gives us 27. And of course, that's 3, so the answer is 1/3. This is, in general, it's a good idea when you have negative exponents to make use of this rule here, so that you can say 27 to the minus 1/3 is 1 over 27 to the 1/3, reduce it to positive exponents, and then handle it the traditional way. Okay, now, what do we mean by something like this? Say we're worrying about 9 to the 3/2. Okay? So far, all the fractions that we've considered had numerators of 1, all the fractional exponents. The numerator of the fraction was 1. 9 to the 1/2, 9 to the 1/3, and so on. Okay, now, according to this rule, if we want this rule to continue to make sense, a to the r to the s is a to the rs, we could think of 9 to the 3/2 as 9 to the 1/2 cubed. This is a to the r to the s is a to the rs. I'm using this rule over here. We want this rule to hold true. Therefore, 9 to the 3/2 is 9 to the 1/2 cubed. Okay, this could be thought of as the positive square root of 9 cubed. The positive square root of 9, of course, is plus 3. 3 cubed gives us 27. Okay, now, you might say, well, why can't you think of 9 to the 3/2 as 9 cubed to the 1/2? Well, the answer is you can. 9 cubed to the 1/2 would still be 9 to the 3/2. It's a to the r to the s is a to the rs. The only difference is that it's a little harder to evaluate this. This means I must cube 9. 9 times 9, that's 81. 81 times 9, that's 729. Having multiplied 9 by itself 3 times to get 729, I then need the square root of 729. Okay, which you may or may not recognize. Now, you may or may not recognize 729 as a perfect square. It turns out to be 27 squared. 27 times 27. Okay, when you multiply, you do get 729. Okay, which I had to go over to the side to do. I had to take the square root of 729. Now, I happened to see the answer, and I knew it, but most people don't recognize, say, 729 as a perfect square. Turns out you do get the same answer, but this is a far easier way to handle the problem. So in general, I would say that while a to the m over n could be thought of either as a to the 1 over n to the nth power, or you could think of it as a to the m to the 1 over n power. This means the nth root of a to the m. This means the nth root of a quantity raised to the nth power. I would think that this is a preferable way to evaluate it. This, you first have to take something, raise it to the nth power, and in doing so, you may or may not recognize it as a perfect root. Okay, so it's preferable to think of it this way. Okay, and to take this sort of as a definition. Of course, they're all the same, but this is, I think, a slightly easier way to work it out. 9 to the 3/2. Think of it as 9 to the 1/2 cubed, and it works out very nicely. It's exactly equal to the square root of 9 cubed, but the work is a little more involved in the latter case. Let's try some more problems. I'd like you to try to work out 64 to the 3/2 and 64 to the 2/3. Okay, if you'd like, you could shut the machine off, try them, and after you've completed these problems, turn me back on and see how you've done. Okay, we're going to use the rules that we have for exponents, what we've done over here. As I said, I'm going to do it in this way. Okay, so I will write this as 64 to the 1/2 cubed. That is the positive square root of 64 cubed. 8 cubed, which is 64 times 8, which is 512. Over here, 64 to the 2/3. This is 64 to the 1/3 power squared. That is the cube root of 64 squared. The cube root of 64 is 4, since 4 times 4 times 4 gives you 64. 4 squared, or 16, as an answer. If you'd like, you can think of the denominator of the fraction indicating the root that you're taking, being the index and the radical sign, and then the numerator telling you what power to take it to. So this is the square root of 64 cubed, the cube root of 64 squared. Okay, let's try a slightly more complicated problem. Let's take minus 8 to the minus 2/3 power. Okay, now, don't get upset when you see something like that. Simply use your rules for exponents one at a time. First of all, anytime I have something to a negative power, I prefer to think of it as 1 over that something to the positive power. So I will start by saying this is 1 over minus 8 to the 2/3 power. At least now I am dealing with a positive rational exponent. Minus 8 to the minus 2/3 power is 1 over minus 8 to the 2/3 power. Now, minus 8 to the 2/3 power I can think of as minus 8 to the 1/3 power squared. The same way I did it over here. The 2/3 power, 64, it means the cube root of 64 squared, or 64 to the 1/3 squared. The same thing here, minus 8 to the 1/3 squared. That is 1 over the cube root of minus 8 squared. Now, the cube root of minus 8, of course, is minus 2, and that is to be squared, so we get a final answer of 1/4. So although it looked very terrible, it worked out fairly simply. The trick is not to try to do it all at one time, okay? First, you can remove the negative exponent by bringing it into the denominator, and then worry about the fact that the power itself, okay, does not have 1 in the numerator. Break it up so that it does, take a root, and then take the appropriate power at the end. Let's try some more examples. X to the 1/2 times x to the 1/4. Remember, the rules that we've had before, a to the r times a to the s, is still going to be a to the r plus s, whether they are natural numbers, integers, or now rational numbers. Same rules, going to hold true. You can see why this is preferable to having different rules for different sets of numbers. We will keep the same base. We will add the powers, 1/2 plus 1/4. 1/2, of course, is 2/4 plus 1/4 gives us 3/4. So x to the 3/4. How do we add fractions? We combine over the same denominator. We first have to build a fraction equivalent to 1/2, namely 2/4. It has the same denominator as the fraction 1/4. 2/4 plus 1/4 gave us 3/4. If there was something to be evaluated here, this could be thought of as the 4th root of x cubed. Okay, how about x to the 6/5 power raised to the 5/2? All right, this is like a to the r to the s. It's a to the rs. In other words, we multiply the powers. We have 6/5 times 5/2. We can cancel the 5s. 2 divided by 2 gives you 1. 2 into 6 goes 3 times, giving us a final answer of x cubed. And for our last problem, let's try x to the 3/4 over x to the 2/3. Okay, this is an example of this rule over here. You've had this before, but not with rational exponents. You're dividing, you keep the same base, and you subtract the powers. 3/4 minus 2/3. In order to be able to subtract these fractions, we would like to have the same denominator. So we build fractions equivalent to these that have the same denominator. The lowest common denominator here, of course, is 12. It happens to be the product of the denominators. So we say we'd like to turn this into some number of 12ths minus some number of 12ths. 3/4, to go from 4 to 12, we multiply by 3, so we also multiply the numerator by 3. 3/4 is equivalent to 9/12. Okay, minus 2/3, so to go from 3 to 12, we multiply by 4. We also multiply the numerator by 4 to get 8/12. X to the 9/12 minus 8/12, or x to the 1/12 for the answer. And this brings us to the end of the tape.